Yeah, thank you for this opportunity.
So I will now like to welcome our next speaker, who's Gertz. He's a principal consultant and CEO of Northwind Engineering in Estonia, and which is this company was founded in 2017. But his background, it's in the different years in the Danish wind industry in terms of aerodynamics, both at Siemens and at DTU. Just a moment that I will now we should be able to see a message.
Yes, can you hear me?
Hi, nice to see you. Welcome.
Thank you. All right, I'll share my screen here.
And meanwhile, of course, if someone has some question, they can always put it in the chat, and then maybe previous speakers can reply that. That's also a possibility, of course. Yeah, we see the screen.
Great.
Perfect. Floor is yours.
Great. Thanks for inviting me to give a talk at today's conference. I think this is quick becoming one of the go-to conferences of the year for small and medium wind turbine community. So keep up the good work. I'm going to talk about how we support small and medium wind turbine manufacturers with modeling and design services. So just an outline, I'll give a brief introduction of our company and the team, and talk about some of our main tools and capabilities, and then just talk about some project examples to give a better idea of exactly what we do for our clients. So we've been around since 2017, as Daniel mentioned. Prior to that, I was working at Siemens Wind Power and the Danish Technical University in Denmark. We have happy, smiley customers all over Europe and in North America. And our bread and butter really is aeroelastic modeling. More recently, within the last year, we've started offering CFD services, which we'll talk about later. And we also do some structural analysis and mechanical design. And you can see here just some figures to give you an idea of the type of work we've done and the number of projects we've done. So we're up over 40 now, quite proud of that. And here are some of our happy clients. So, team. As Daniel said, I'm Drew, and I have specialty in aeroelastic modeling, previously in the Danish wind industry, and now running our consultancy. We also have Ali, who is specialist in CFD. And we are the only two salaried employees at the company, but I like to say that we have a deep bench, if I could use a sports term. And that is a network of other independent consulting professionals who we bring on and partner with in quite a lot of projects to fill out any missing competencies we might have to really offer a complete suite of services to the client when they need them. So, as I mentioned, we have a heavy focus on aeroelastic modeling, and we use FAST and OpenFAST as well as HawkTwo. And we feel that the combination of having these two codes in our toolbox really covers the majority of the small and medium wind turbines that we encounter. The different features that they employ, you can do vertical axis turbines in HawkTwo, plus we can cover active, passive yaw, tip brakes, furling, tail fins, plus all the standard things you have to consider when you're running an aeroelastic model: flexibility, structural dynamics, turbulent inflow, controls. So with these two codes, we're usually able to meet the needs of our clients. Now, another thing we're big into is tool development. So we have a automated simulation setup, execution, post-processing environment that we've developed in Python. So we will develop the design load cases and the simulation input files based on the standards, execute them in parallel, on our cluster and then do the automated post-processing. And we produce these standard reports, which provide the extreme and fatigue loads as well as power curve. So one of the main results or main deliverables is usually the loads table for the client, whether it's for design loads or for certification purposes. So that's always in there. But we also like to add these additional plots to really give better insight on the loads envelope and the effect of different load cases and different simulations in particular. Now, one big part of the aeroelastic modeling process, which isn't shown here, is actually the analysis. So after you run the simulations, you might have 500, you might have 1,000 simulations, and you have to be sure that they've all that the behavior of the turbine is realistic in all these simulations. So you have to dig into the simulations, and we developed a tool to do that as well, which I just want to quickly show you because we're quite proud of it, but also because I think it could be interesting to some potential clients. So, for example, this is a web-based app that runs on our simulation server, and we can choose one or several design load cases, and for example, the load channel, and it quickly produces your scatter plots of your min, max, mean, plus top 10, bottom 10 loads, and the distribution of the extreme loads across the load cases. So if I was to select all the load cases, then you can see for every load case, we have the minimum, maximum. So it really helps you identify which load cases are driving your loads. And if you're still designing your turbine, you can even work on modifying your design or your control system to try to knock off some of these extreme loads and have a more loads efficient design. It also helps to identify outliers. For example, in the plots, if we can click on any point and it will generate, or it'll load the time series for that simulation. It should just come up in a moment. And of course, classic demo crash. But anyways, I just want to show this quickly and mention that I feel like this could be useful also for prototype and loads validation campaigns and potentially monitoring of fleets, even digital twin applications for maybe larger scale turbines. So anyways, just a quick little demo of that. Now we'll get on to some project examples. This one is very interesting, a vertical axis turbine with some flow guiding sails, as they're called. The goal of the project was to develop the design loads. And so we had to come up with an approach that sort of met the spirit of the standards, despite the unique design. So what we came up with was to run CFD to generate the aerodynamic loads, and then leverage the simple loads model for vertical axis turbines from the Japanese small wind turbine standard. Now, there was an English version available, so we had to add the competency of Japanese translation to our toolbox, but it all worked out, and we had to make some small adjustments to the model to represent this Savonius turbine, but in the end, we were able to produce a loads set that basically covered all the load cases in the small wind turbine standard. This is another unique design, the Kite X turbine. It's a very lightweight, designed to be a portable turbine, and because it's so lightweight, they have to use these tethers to stiffen up the structure. So this was built up in Hawk 2, and in addition to the unique structure, it has active pitch and variable speed with cyclic pitch. So not only is the blade pitching depending on the rotor speed, but it's also pitching with the azimuth angle. So this called for some custom controller coding in Fortran to implement that cyclic pitch algorithm. And this is a plot we typically produce for controller tuning purposes. It's the response to a staircase wind profile, and we show the rotor speed, the pitch angle. You can see the cyclic pitch overlaid here. as well as power and yaw angle. So this is an example of some more conventional turbines, three-bladed upwind horizontal axis turbines, variable speed, active pitch. So the turbine on the left is from Codair and on the right from Pecos. We built the models on OpenFast and produced design loads. In the case of Codair, we also supported blade structural verification and the bolted connections verification. With Pecos, we were involved right from the early going, so we were supporting the conceptual design, that evaluating different combinations of rotor size, rotor speed, different features with and without, say, pitch control, for example. And we had implemented some modification to the OpenFast source code to represent some features that they were interested in considering. This one was a more kind of end-to-end project. So we were involved right from the conceptual design all the way through to the manufacturing, at least the manufacturing drawings. So this is the Estonian Tuga design with a tail and tip brakes. So the tip brake model is not yet available in OpenFast. So that's why we had to use Fast 7. But we designed some of the components, the hub, did the stress analysis, and then followed through with the manufacturing drawings. These two projects here, I've kind of lumped them together because in this case, we actually developed the aeroelastic model and then handed over to their in-house team, who then kind of proceeded further, and we just provide ongoing support whenever they need any help. But they're running their own simulations. So on the left is a Canadian turbine furling machine, and on the right is the EOCycle, the two EOCycle models that were simulated in HOP 2. This is another Tuga turbine. In this case, we were asked to do the simple loads calculations and support their certification, which involves prototype testing. So we developed Python code to visualize the measurements and help optimize the control settings for power curve optimization. We also did some structure analysis for them in support of the certification. This is the RISE downwind two-bladed teetering turbine. We did the Fast 7 model and also supported on blade structural verification. So this involves determining the material properties, the 95% probability and confidence levels, establishing safety factors depending on the manufacturing process and so on. And then we did an analytical stress evaluation where we considered the different laminates separately and checked on in the end, the stress reserve factor to show that it would pass for certification. And I have one more slide. This is actually a plug for one of our partners who we work very closely with. Unfortunately, can't be here today, but we have a real complementary set of services and we work together quite often. So on our side, we can do the design and modeling, and Joseph Sposi from RE Innovations fills in the certification, planning, and testing, and actual certification. He's been doing this for 15 years now or so, and we've worked quite closely together. So that's the end of my talk. I don't know how long I took. I should have looked at the clock, but I hope you enjoyed it, and I look forward to any questions you might have.
It was perfect timing, thanks. And also thank you very much for your kind words from the beginning, because it is actually true. We see it becoming more and more interesting for people to join And so you mentioned Kitex, Viking, Pecos, right? Energy. They've all been presenting at the conference. So that's we hope that this can help also developers to do business among each other. Questions from the audience? Comments from Neil? No? You are clear? So, oh, there is a question. Yes, David.
Yeah, of course.
Okay. Can you hear me? That's
Yeah.
my question. Thank you, Drew. What I find really interesting and exciting about what you're talking about is the general increase in technology level that's coming into small and medium turbines. Because I don't think, to put it bluntly, 15 years ago, you wouldn't have been able to make a living out of this.
That's for sure.
Have you got any general comments on that feature of it, and where do you see it going?
In terms of the technology that's being used nowadays.
Or just any aspect of it, because I mean, one of the really nice things about small wind turbines is a great diversity of technology and architectures. So you can take that question any way you like.
Yeah. Well, one thing I've noticed is, there are different philosophies that different companies have. So some people prefer, max kind of focusing on simplicity, not so many moving parts, not so many features, although you do pay a price on performance usually. And then, you have other companies that are happy to implement the features that you see on industrial scale turbines, pitch control and variable speed and so on. And it seems to me, if you have conviction with your choices, then they're usually able to make them work. So I don't necessarily see one approach as being better than the other, but you can make it work whichever direction you go, but you definitely have to you have to be sure, you have to check all the boxes in terms of your design and your features, and making sure of the structural and lifetime considerations. But I do think it's possible, and we are able to produce the data that they need to then design high quality, reliable turbines.
Okay. As a follow-up question, what is there a sort of closing of the cycle involved with this? That you showed some very innovative designs that you've worked on, and they presumably are pushing the fidelity level of your simulations. So are you expecting to get feedback from the performance of those turbines to improve your modeling capacities?
Yeah, so that's definitely the biggest hole that we have is validation data. So we oftentimes do have to produce models without any measurements to validate against, which is tough, and it introduces uncertainty. And we're always sure to communicate that to the client. But actually, a lot of these projects, we're finally getting to the point where the prototypes are going up and the measurements are coming in, and so I'm always pushing the clients to could you add one more sensor to your prototype, just to validate our model a little more. But these are long-term projects, so oftentimes our involvement ends, and then a year or two later the prototype goes up. But luckily, the models we use, we do have validation data for some turbines, so we can at least have confidence in our approach. But the validation data of the specific designs themselves, I'm definitely looking for more.
Thank you.
Thank you very much. There is a question from Niels Christian Olsen. If you have tested fault dispatched from Netherlands. True. Not muted, right? No. True.
Oh, sorry.
Yeah, there was a question. There is a question in the chat for you. If you have
Oh,
tested.
sorry. Have we tested Fortis Passat? Or have we modeled? I have not been involved with this turbine, if that was the question.
Okay. So thank you very much for the presentation, and we hope we have the chance next year to see you in person at the conference.